the third.
Yeah, that's the third.
Not checked. Okay. So okay, so we want to show the following theorem. Let's suppose that so omega is open and bounded. Suppose that U is in C2 omega and continues up to the closure, and minus Laplace of U. Okay. Then this is what we want to. I think this is the statement, the last statement of yesterday. Yes. Okay. So suppose that so take epsilon positive, define V of x this function here for any x. So I have my function u, which is in some sense not really, right? But in one dimension it would be convex, say. And I make it more convex, in some sense, adding this parabola this way. So let us compute minus Laplacian u, minus Laplacian v, sorry, minus Laplacian v.
Equal to minus Laplacian v.
It equal to minus Laplacian u minus epsilon, and this Laplacian is n in n dimension, right? Because so the is this okay?
Yes.
It's okay. Now this is strictly negative. Okay. Then for such a kind of function here, then say v cannot have a maximum point in omega, or also the supremum hence sup v in omega is also equal to the sup v boundary of omega. Why v can, do you see this? Why v cannot have a maximum point in omega?
Because of volume main volume.
So suppose x bar in omega is a maximum point. Okay. What can we say? Huh? We don't, I mean, we have function v is C2, v is smooth, because v is a C2 function plus something which is a polynomial. So it's perfectly smooth. So why don't we use the PDE? No? So what can we say about what happens at the maximum point on the Laplacian on V? At the maximum point is less, strictly less, or so remember, at the maximum point, the Hessian
is maximum point is in maximum point is the second the Laplacian, you know, actually second derivative is smaller than 0, like less than 0. Is
smaller than or equal than 0. No? So minus Laplacian at the maximum point. And this is a contradiction with this. Okay, impossible. So for this, I mean, this is okay. Now, so we want to show what we want to show. This, no? We want to show that sup of u in omega is less than or equal to sup of u on the boundary of omega. We want to show this because since sup is immediate, okay. Do you agree with this? So to prove this equality, one inequality is immediate, is this one. So what we really have to show is so let us concentrate on this. So take a point, say z, y, in omega, and consider u of y. So uy is equal by this expression is equal to v of y minus epsilon square y square. Okay, which is less than or equal to the supremum of v in omega plus some epsilon times a big constant, because omega is bounded, no? So if I compute the supremum of y square over omega, is this big constant. This is what is the supremum of v on omega. We have this this is equal to this because it is written here. Okay. Now this supremum, if you remember the definition of this, this supremum is less than or equal than the supremum of u on the boundary of omega plus epsilon some other constant. Okay? Supremum of u plus epsilon, there is some other constant here, epsilon another constant here, so at the end some constant like this. Because omega is bounded, and the boundary of omega is bounded, everything here is bounded. So this shows that for any y, this u of y is less than or equal than this. This is a finite number, right? Because u is continuous and this is compact. So I can pass to the supremum with respect to y, and we get the same inequality. C is independent, is an absolute constant, capital C prime. C prime is an absolute constant, is independent of epsilon. So now it is sufficient to let epsilon to 0 plus in this inequality. To get what we want. Is this clear?
Yes.
Are you convinced? Okay. Okay. Okay, so this is the interesting result. We have already seen such kind of result in the variational approach. Okay. And now, yes, I would like to do some consequence of. I think that you have done the exercise I left yesterday, concerning the comparison. It's enough to take the difference. No, you have a subsolution, super solution. You take a difference. This is a subsolution. You apply this. You immediately get no. That's very easy exercise. So take. Now we want to talk about regularity. Regularity of harmonic functions. So theorem. So let omega be open set. Suppose that u is continuous and u of x, and for any x for any rho say smaller than the distance between x and the boundary of omega, is the omega. For any rho, such that this, we have that u of x is equal to the surface, its surface mean value on the boundary of the ball center. So u at the center here is exactly equal to the mean value of u itself on the boundary. So I have written u continuous for the same reason that we discussed yesterday. In order to give a meaning to a surface integral, we can do this if u is pointwise everywhere defined. So if it is in L1 loc or in L1, I cannot tell this. But if it is continuous, this is defined the value at each point. This has zero level measure, that doesn't matter. This is a mean value. Do you agree with this? Or you don't? It's fine? Then u is infinitely smooth. It's infinity. In particular, if u is harmonic in omega, well, if u is harmonic in omega, we know that this property holds. We have seen yesterday, do you remember? We have proven this in two different ways. Okay, so for an harmonic function, we surely have the surface mean value formula. Harmonic function is continuous. Actually, C2. Okay, so if u is harmonic, then u is infinity. Okay, so in particular C yesterday. If u is harmonic, then u is infinity. Now, if it is infinity, we can differentiate u. So, and then in derivative, so moreover, if you have any multi-index, say alpha is equal to alpha 1, alpha n, and you indicate by this symbol the alpha 1, the x1 alpha 1, the alpha n, the xn alpha n u of x. So any combination of derivatives in variables given by a multi-index like this. No? Is this clear? What is this? Yes. Is this notation okay? Then grad alpha u is harmonic. Okay. Can you prove this? Are you able to prove? I mean, u is infinity, so we can differentiate. For instance, we can take the gradient. Say, for example, d over dx1 of u. U is infinity, so I can differentiate, and this is still infinity. I claim that this is harmonic, if u is harmonic. So what should I do? I have to take minus Laplacian of this, and then well, what happens when I can exchange?
Yeah.
No? And then if it is harmonic, this is 0, and therefore also the derivative is 0. Okay? In particular, you will see that once we know that the gradient, for instance, is harmonic, then we have a surface mean value formula or a volume mean value formula not only for u, but also for the gradient. Okay? So, let's see. So, the real statement concludes here. So I erase what is written here, I concentrate on the proof of C infinity matrix. Okay. So define omega, so given epsilon positive, define omega epsilon minus just this set. So what it is just the set omega reduced a little bit by epsilon. Let's see. Suppose that this is omega. Okay. Then I take the set of all points inside omega, having distance from the complement at least epsilon. So if this is epsilon, just a reduction a little bit thinner omega, okay? So now take rho epsilon, stand sequence, a sequence of radially symmetric modifiers, the standard sequence of modifiers. Okay. Symmetric modifiers. So this, I think that you should know what is this, right? So this is a smooth function. Yes. So these are positive and negative functions. The integral for any epsilon, they are supported in the ball of radius epsilon. Huh? The integral of each rho epsilon is normalized to 1, and they are radial. So radial, positive, C infinity smooth, and supported in the ball of radius epsilon. Okay? Okay. So now what do I do? I consider the convolution. Rho epsilon is compact support, so we can do the convolution. So, and I take this convolution, but I can take it only. So the support of rho epsilon is ball of radius epsilon. So I can define such a convolution only in omega epsilon minus, because if I choose a point here, then the ball goes outside, and here u is not defined anymore. Okay? So if I want to define this object is defined only for x in omega epsilon minus, because of the... So for any x in omega epsilon minus, this is defined. Okay. Okay, so this is u of y, rho epsilon x minus y, dy on the ball of radius epsilon centered in x. Okay. Now, this is a sequence, is a radially symmetric modifier, so let us write rho epsilon of x as rho epsilon of normal tilde, say, rho epsilon tilde of normal x, okay? Because we are assuming symmetry with respect no? Something which depends only on the norm of x, but does not depend on the angles. So this integral is not anymore an integral over Rn because the support of rho epsilon is contained in v epsilon x. Okay. So this is equal to the integral v epsilon x u of y rho tilde epsilon x minus y dx dy, sorry. Now what we could do is to integrate by slicing. No?
Okay, yes.
So we can integrate from 0 to epsilon, and then we are integrating on the ball of radius s centered at x u of y, and then we have rho tilde epsilon. Now y is on the boundary of the ball centered at x with radius s, so this is s there, okay, and then, sorry, to erase. Is it okay? Can I go on or not? I think you are not so.
I'm just thinking of the rho cap, still remaining rho cap epsilon. I thought it should be cap s of s.
No, I have not understood the question.
The rho cap. This row, yes.
Yes.
I want to understand why we are defining why it becomes rho epsilon of s.
Of s,
Yeah.
yes, because there is a tilde here.
The tilde.
So this integral on the volume ball, on the fat ball, I integrate on each concentric surface.
Yes.
Okay. So fix s. Fix this is s now. Fix one of those concentric balls. On those concentric balls, if y is here and x is here, this distance is s.
This is, yeah.
That's it. Simply this. Okay. So what do we have here? So we have 0 epsilon. Then we have so tilde epsilon s. Then we have the integral on the boundary of Bs centered at x. And then we have u of y, and then we have dHn minus 1. Okay. And now I start to use my assumption. I am using my assumption.
Mean value?
Ah, yes, it is written here. I have this assumption. Okay, so this actually is. Now I substitute the following. I know that on the boundary of the ball of radius s, the mean value, sigma n minus 1 s to the n minus 1 of u of y, this is by assumption u at the center. Okay? This is by assumption. So this means that I can substitute this, and this gives me u of x times this number. Now u of x is independent of y and s, so it goes outside. This number is also independent, just depending on the dimension. But what remains here is 0 epsilon rho tilde epsilon s rho tilde epsilon s to the n minus 1 ds. Okay. Okay, and now I want to go back. So what happens if I compute the integral on the ball of radius x? So let me compute this integral that I know to be 1. Sorry, u epsilon y minus x dy. I know that this is equal 1, but this is also equal to integral from 0 to epsilon, so rho tilde epsilon s integral of the boundary dsx d h n minus 1 ds, right? The h n minus 1 y ds for the use of the same trick. So I integrate by slicing this. I put the tilde. No? Okay. So this is what? Now this is what? Is the integral from 0 to epsilon of rho tilde epsilon s, and then I have the n minus 1 dimensional surface measure of the boundary of the ball of radius s, which is sigma n minus 1 s to the n minus 1. Huh? And I know this is equal to 1, because this is equal. These are standard modifiers, and as you said, this is 1. So this is 1. And so this means that this is equal to u of x. So if you look at what we can conclude about this computation, we have shown, so let me erase something because otherwise there is no space. Conclusion is that u star rho epsilon is equal, actually so rigid that it is equal to u itself on omega epsilon minus. Okay?
Convolution has better regularity.
Of course, now we know that you should know that this is infinity. So this implies that u must be C infinity of omega epsilon minus. But this is true for any positive epsilon. And so what does it mean to be C infinity? You take a point, around the point, you inside omega, you are C infinity, and so this means that if you take a point in omega, there is small epsilon, small enough, so I have my omega, I take any point, and then I take epsilon small enough, so that omega epsilon minus is this, so in this ball U is C infinity. Hmm? Okay, so this is quite strong result. It is, you see, we crucially use the Laplacian. We cannot change operator. We cannot, with this argument is based on the surface mean value formula. And the surface mean value formula is something that we have proven just only for functions which are harmonic. We cannot change the energy into some strictly convex integrand. We cannot say. So this is specifically true for this kind of argument. I mean, this kind of argument works for that operator. Okay. But in any case, it's very surprising in some sense, because you have a function which satisfies this combination of second derivative equal, a C2 function which satisfies this combination of second derivatives equal to 0. So, at the first look, I mean, to deduce from this that you are C infinity is not so immediate, just C2. Plus some certain combination of second derivatives must be 0 everywhere, then C infinity. It's not immediate. I don't think so. No, that it's so direct. So this is a regularity result, which it's very nice. And now I want to show you something more delicate than this. So today we are working about regularity. We are discussing the regularity problems. So now we have C infinity for an harmonic function. So from C2 we go directly to C infinity. Actually, we can do more. So there is this theorem now, this fundamental theorem, I would say, is called the gradient estimate. So suppose that omega is an open bounded set. Define here for any x in omega, define the function d omega x is the distance from x to the complement of the open set. Okay. So if this is my omega, I take a point. The d omega x is this distance from the complement, okay? So let u be harmonic. Actually, if it is C2, it is C infinity by the previous result. So now let alpha be a multi-index. Then, let's see if I write So we have this. Supremum u in omega. Then there are constants here. So suppose that the length of the multi-index, so alpha is alpha 1, alpha n. So it's an n-tuple of natural numbers. Okay. This symbol has been defined before, just 5 minutes ago. The length of the multi-index is just the sum of these natural numbers. So let me call it k. So then setting k so here there is a constant depending on n and k, and here there is the distance at k. Now I have to check the constant. So for any x in omega, where Cnk should be, and okay, let me check. Let me check the constant. Yes, it's correct. It seems to be correct. So this is a very, very strong estimate, which pretends, at least when we are not too close to the boundary of omega, so when this number is not close to be 0, so inside, say, it pretends, say, to bound all derivatives just, okay, derivatives of order, say, 1, for instance, for the gradient. This is, and this is the dimension of the space, this is k equal 1, say. It pretends to bound the gradient of u with the supremum of u, which is, for a generic function, is impossible. It's impossible to control the gradient of a function with the function itself. In general, it's impossible. But for this, even more for second derivative, third derivative, and so on. And this kind of result has a lot of consequences. It's extremely important in PDEs, in the theory of harmonic functions. So now the proof is not easy, so we will try to prove it now. Is the statement clear?
Yes, but so if we know that U is harmonic, also the supreme is can be taken on the boundary.
The supreme can be taken
On the boundary.
Oh, I have not written here, by the way, I have not written that U is continuous up to the boundary. So this supremum could be in principle also plus infinity. If it is plus infinity, there is nothing to prove. Okay. If there is plus infinity, there is nothing to prove. Okay, so proof. So as I said, if it is supremum, so we can assume the supremum is finite. Otherwise, there is nothing to do. Okay, so let us start with the case k equal 1. Okay. So suppose that k is equal 1. So we have just one index, say, d over d over d something. So So we know, what do we know about, so let me call this alpha, so alpha is just only one, all are 0 except for 1. Say, let me call this alpha maybe. Okay. And we have that this function here this function here is harmonic. Previous comment, no? So this is the previous theorem. So for this we have a mean value formula. So we can write so given x for x in omega and the ball b rho x, say, with our usual notation. So we have x and rho here. Okay. Rho is strictly smaller, the boundary does not touch the boundary of omega. So, what do we have? We have that this satisfies the mean value formula, so we can write the Gauss mean value formula. So the gradient alpha of u is equal to 1 over omega n rho to the n integral b rho x dy. Okay. So now the idea is, as usual, to use the Gauss Green, the divergence theorem. So how should I use the divergence theorem? Consider, so now alpha is in between all this alpha I, okay. Alpha, say, is from 1 to n. One of the components. So consider the vector field eta of x. So let me call this alpha. For me, it's better if I call it I. Can I call it I, just one of the components? It's easy. Notation. Okay, so eta I, so eta of x, let me indicate this vector field here. This is the ith vector of the basis. So, and this is equal to 1 over omega n rho to the n integral b rho x d over dxi u of y dy. Okay. Okay. So, what is the divergence of eta? So this vector field is just in the direction I, and all other components are 0. So this means that when I take the divergence, I have to sum the derivatives, the jth derivative with respect to xj of the jth component. So this is just reduces to just b over dxi. Just to this. Of course, EI is a constant vector field, so this is just d over x. Okay, d over dxi u of x, u of x.
Sorry, I have one question. What is K? Actually,
K is the length of the multi-index. This is called the length of the multi-index. Just I could avoid to use K, but that's for simplicity. Okay, just the length of the multi-index. So we have this. Therefore, this is a divergence, no? And now we can use the Gauss theorem. So this is equal, so to 1 omega n rho to the n. Sorry, this is X. This is a divergence, so this becomes an integral over the boundary. And then we have the scalar product between the vector field and the outward unit normal. So we have u of x, and the vector field is this multiplied by the outward unit normal. This means that we are taking the outward unit normal. So this is u of y, sorry, u of y, evaluated at y, scalar product with ei, so this is just the ith component of that vector. Okay, so it's a little bit heavy as a notation, but let me put here, I here. dHn minus 1. Okay. So let us keep only this formula. So this is equal to this. So I erase everything. These are equal. So this must be equal, and therefore if I take the absolute value, this is surely less than or equal, then put the absolute value inside. Now I can take the product, this is at most 1, because it's a unit vector, just one component, so it's less than or equal than 1. And so if I use the supremum, what do I get? 1 over omega n rho to the n. Then I have the supremum of absolute value of u everywhere, say on the boundary of the ball, but maybe I can do even the supremum everywhere. It's very rough now. Let's see what happens. And then I have, I put this 1, so this becomes 1. So let's see, what do I get? I get 1 over omega n rho to the n. Then there is sigma n minus 1, sigma n minus 1 rho to the n minus 1. And then I have the supremum of absolute value omega. Remember that sigma, we always have to remember that this is equal to this. So what do I get? Let's see if it is consistent with our constants. So we have n, omega n cancels with this, n over rho, sup, omega absolute value. Okay, now we want to minimize, we have some room to work because we have, this is omega, this is x, and we have an estimate, and we are using rho. But we want to make the right-hand side as small as possible in order to improve our estimate, because this is the right-hand side, no? This is less than this. How can we work by making this, which is the only degree of freedom that we have in order to reduce this right-hand side as most as we can. Working. This is fixed. This is fixed, but we can. I mean, x is fixed, but we can, in order to reduce the right-hand side, we have to enlarge rho as most as we can. Okay. No. So now, if you want, we can. So this is rho. Rho will be just a fraction of d omega of x. So rho is just a fraction of the wall distance. Now remember, d omega of x is this. Is the distance from the boundary. Okay. Rho is just this radius. So it means that rho is a multiple of this distance where this multiple is less than 1. Okay? So lambda is 1. Okay. This is surely true. So we can put in place of rho, we can put this expression here. And now we can let lambda to 1 from the left. So letting so we make as large as possible, which simply means that we are taking, I mean, somehow enlarging the radius as most as we can. Somehow, no? So we let lambda to 1 plus, to 1 minus, sorry, and so the left-hand side does not depend on alpha, so we have that the gradient d over dxi of u at any point x is less than or equal than n d omega x supremum of u. And this should be exactly, so since you see k is 1, so this is 1, and Cn1 is n. So n, okay. So we have our estimate, at least for the gradient. And now the idea is to do the gradient of the gradient and so on, which is not so immediate, unfortunately, but at least, so for k equal 1, the theorem is proven. Okay, and now the idea is to work on induction argument on k. Let's see some detail on this. So is this clear up to now? So this is called gradient estimate. We estimate the gradient. Of course, the estimate becomes worse and worse, when this rho is very small. As soon as x is very close to the boundary, the estimate becomes bad. But this is the estimate that we have. So let's go on now. So now the idea, as I said, is to use induction on K. So suppose that for alpha equal k, we have that grad alpha ux is less than or equal than k to the k and to the k the omega x to the k sup. So now take a multi-index one more. So let me fix a notation. So take a multi-index beta and of length k plus 1. Okay. So and write so that so grad beta. So let me write this d over dxi alpha u of x, where alpha has length k, so that we can somehow reduce to our, okay? I mean, it's more or less clear what we want to do. This is the new u. This is harmonic, so it's the new u. Before this was just u. And now we want to do the same as before. So we write the volume mean value formula for this. Okay, let us write it. So we have that is 1 omega n rho to the n. And then we use the Gauss as before. This is a function, d over the alpha 1, etc., 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 dy. So we use the vector field eta grad alpha u y I as before. Exactly as well. This is actually a function, scalar function, no? Okay. So exactly as before, this using the Divergence Theorem becomes the integral of the boundary here of what? Of grad alpha ux, and then we have the again the outward unit normal from I component at y dh what? Okay, and now I think that we just have to do what? So we take the absolute value and now we do as before, we argue as before, the integral 0x, and now we have this quantity here. But this multi-index has length k, so k equal 1 has been proven, is the first step of the inductive argument, is proven before. Now we have the inductive assumption. So this is less than or equal by the inductive assumption of 1 omega n rho to the n. Then we have the integral, boundary of the rho of this x. And now we have this. Okay? So let me write also the supremum outside. then we have also the constants, so k to the k, n to the k are outside. And what remains here is b rho x 1 over the omega y dh n minus 1 of y.
Y raised to power k.
Hmm?
The rho of y raised to power k.
The
The
rho.
rho of y raised to power k. There should be
Ah,
power
thank
k.
you. Yeah, yes, sorry. Thank you, sorry. This was a mistake. I forgot the k. This is. So which is the situation now? This is our omega. We have a point, x. This is rho. Then we have point y here. Okay. So d omega x, the distance of x from the boundary of omega, the distance of x from the boundary of omega is, by the triangular property, is less than this distance plus, this distance plus the distance of y from the boundary of omega. So this is less than the distance of x from y and the distance from y from the boundary of omega. So this is less than rho plus the omega y. Hmm? Okay. So this, so d omega y is larger than or equal than something. D omega y is larger or equal than d omega x minus rho. And again, we can write rho as before. Rho is just a portion of this. For some lambda in 0, 1, this is exactly for some lambda okay. So this means that we have d omega y larger or equal than 1 minus lambda, which is positive, d omega x rho is right. Okay? Huh? Okay, so this, why I'm doing this? Well, because I have the problem of this integral here, and this y dependence here is bad. I cannot integrate easily this. But if I put an x, then this goes outside. Because I am integrating y. But if I could put x here, this goes outside. I cannot really do this, but with this trick, 1 over d omega, you see, now what do we get? So I think that I can erase, yes, this I can erase, right? This I can erase. So with this trick, what do I get? I get that 1 over d omega y is less than or equal, where is my lambda? Here. Is 1 over 1 minus lambda d omega x. Okay. Okay. So where do I am? Let's see. Because so now,
You raise to the power of k.
Then I have to, yes, if I want to continue my inequality, so now I erase where? Now this is the assumption, so I can erase. This, I think I can erase also this because I have used. Okay. So let me continue the inequality from here. So, as you see, grad beta u of x less than or equal than what? So I have, now I copy these factors. So 1 over omega n rho n supremum u omega k to the k n to the k. Now I put here something larger, so b rho x 1 over 1 minus lambda to the k d omega x to the k, but this is integrated in y.
Yeah.
So I can put this outside and just write the surface area sigma n minus 1 rho n minus 1. Okay, so let's see what's happening here. So I can, so sigma n minus 1 is n omega n, which cancels with this, so n remains. Okay. There is a cancellation rho to the n and rho to the n minus 1, so this rho remains here. Then I have 1 over d omega x to the k. Then I have my supremum on omega. Then I have my k to the k and then to the k. Please, if I make mistakes, because otherwise I check the
we have the 1 minus lambda raised to power k.
Ah, yes, for instance, I forget. So this one, thank you. So 1 divided 1 minus lambda to the k, and then there is something else. Okay, now let us recall that that rho has been written like this. Okay, so I can substitute here. So this rho is actually lambda d omega x. So let me put another lambda here. I cancel this rho. And then I have here k plus 1. Okay, do you agree with this? Now, so this n apparently goes here and this becomes n to the k plus 1. Is it correct?
Yes.
Please, we have to check very carefully, so otherwise, so this is k plus 1. So what would I like to have? So let's see. The thesis. The thesis would be, I don't have the thesis yet, but I would like to have what? I would like, first of all, the supremum of u, and this is there. This is there. This to the correct power is also there. Okay.
K plus 1 is to power k plus 1.
And n to the k plus 1 is there. But I would like to have also k to the k plus 1.
K plus 1 to the k plus 1.
See, yes, sorry, thank you, sorry. K plus 1 to the k plus 1. Which I don't have. But I have, again, I have some degree of freedom because I want to make this as small as possible. Right?
So, if you take f lambda these functions, or you need to find supremum. If lambda.
What I can do, consider the following function. For any lambda in 0, 1. What is this function? Okay, this is a positive function. The idea, in order to make the right hand side, to improve the estimate, to make a better estimate, is to make smaller as possible the right hand side. So the idea is now we can choose lambda, right? How can we choose this lambda? Well, you see, this function, as lambda goes to 0 plus, goes to plus infinity. As lambda goes to 1 minus, it goes to plus infinity. Okay? So we look for lambda min. So this should optimize our estimate. So the idea is to look for the minimizer of h in 0, 1, find it, put it in h, and improve the estimate. Okay, so let's see if we can do this computation. So so I don't want to erase. We are here, right?
Yes,
We are here, right?
the function.
So I don't want, otherwise if I cancel this I'm destroyed, so we have this. Huh? This is what we have. Okay.
And that function.
So now let's see the derivative of h. So h prime of lambda. So it is what? Says lambda square minus 1 minus lambda 2k, and then I have to differentiate. So we have 1 minus lambda to the k minus k lambda 1 minus lambda to the k minus 1. Okay, correct? Huh? It is what? Minus 1 minus lambda to the k minus 1 divided by lambda square 1 minus lambda to the k, it doesn't matter. But more importantly, we have 1 minus lambda minus k lambda. So this derivative is 0 in an interior point. Remember that the domain of A, I cannot take lambda equal 1, because lambda equal 1 is not in the domain of H. Okay. So I have to work inside the interval 0, 1. So lambda min, apparently, is so 1 minus lambda 1 plus k equal 0. So lambda min is equal to this, which is, by the way, correct because it is in between 0 and 1. So this is lambda min. And now we can compute, no? And now we can compute h of lambda min. Is 1 over lambda min, but lambda min is 1 over k plus 1. And then we have 1 minus lambda min. So what is the result of this? So the result of this is what? So k plus 1 goes above. Then we have this object in parentheses, and you have k plus 1 minus 1 is k divided by k plus 1, right? k divided by k plus 1.
Yes. It's k plus 1 to the k plus 1.
So this happens to be k plus 1 to the k plus 1 divided k to the k. Where are we? Here. We have to substitute it here. So let us substitution. So now this is less than or equal, I put lambda min, no? And I substitute, so this is equal to k plus 1 elevated to k plus 1. Then we have k to the k. Then we have the denominator, we have 1 over d omega x k plus 1 supremum. And so fine, because I think that we are done, no? Because we have a cancellation, so there is magical cancellation, and we get exactly what we want. Okay. Now, I want to leave you some exercise based on this test. First, a very, very difficult exercise. Very difficult. So, if you agree, so you have followed all details, right? It is important to follow all details, okay? Now, first, difficult consequence. Well, difficult, yes, it's not easy. So, theorem, so exercise, which is a theorem for the next week, okay? Home is a theorem, it's a famous theorem. So, if U is harmonic in omega, then U is real analytic. What does it mean? It means that at any point x, there is a small ball, small or large ball centered at x inside omega, where U of x coincides with its Taylor expansion of any order. So the series, Taylor series, they coincide. Which is a stronger property than to be C infinity. So not only our solution of the PDE from C2 goes to C infinity, which is already something maybe unexpected, but even more, from C infinity it becomes analytic. No? So this, of course, in 2 dimensions reminds the holomorphicity, no? When you have an holomorphic function, say C1, in principle, then it happens to be analytic. Here we are in any dimension. Okay, so we cannot use the magic tricks that we use in complex analysis in one complex variable. Analytic functions are very special, very rigid. They have this analytic continuation property, all these strong properties. So, why this should be true? I don't want to give you a proof here because now it's time, but how this should be true? You see, we have proven with some effort that we have this we have this estimate, right? Now the idea is that so this is, I mean, something that appears in the Fourier in the Taylor expansion. And this is okay. Suppose that we are far enough from the boundary so that this does not become zero. So we are, say, in a small ball far from the boundary. So this is, say, just a constant to decay. Now this is sort of geometric series. So maybe for rho sufficiently, for r rho sufficiently small, given x in a suitable ball, maybe we can estimate the coefficients of the Taylor series and bound them by a numerical series, geometric series which is converging. So that this is one thing. It's easy to say, but not so easy to prove. Very easy to say, not so easy to prove. But the idea is not terrible, that is there. And now I would like to give you two other properties. Oh, maybe three other properties. One is this exercise. Closure properties of harmonic functions. If UH is a sequence of harmonic functions, and UH converges to U uniformly on compact set, uniformly on compact subsets of omega, then U is harmonic. In omega. Closure meaning that if I take limits of objects in my class, harmonic, I do not go outside my class. The limit still remains harmonic. Closure in this sense.
What was the name?
Uniform on compact sets. Moreover, we can improve the convergence if we have, if we have this convergence, also the gradient, all gradients for any alpha uniformly on compact sets of omega. So from the convergence just uniform on the U, actually we have a much stronger convergence. Not only uniform, but also uniform for derivatives. Okay. Okay. Maybe for today it's enough. So we meet the next week in